Hello students, Jai Swaminarayan. I am Professor Urvish Mewada, HOD Electrical Department, Sri Swaminarayan Institute of Technology, Bhat Gandhinagar. I am the subject matter of Power System 2 subject, which is in the fifth semester Electrical Engineering, and the GTU subject code of the subject is 3150911. Students, we are currently discussing the chapter number 2, that is representation of power system components, and today we are going to discuss the topic number 5, synchronous machine. In last lecture we discussed the different modes of operation of the synchronous machine, that the modes were means the modes that we are use for the operation is normal excitation, under excitation, and over excitation mode. Now today we are going to discuss the synchronous machine and the power factor and power control of the synchronous machine. So from the figure 11 and 12 that illustrated, that we already studied how the synchronous machine power factor changes as the load angle, or we can say phase angle delta changes, the power factor of the synchronous machine will change. So that gives the clue regarding the quantity values Ia and delta, and this can be easily accomplished by the equation Ia cos theta is equal to EF by XS sine delta, where I is equal to V by R. So V is the EF that we get the resultant of V plus the losses, means the terminal voltage plus losses, that is EF, and XS is the synchronous reactance of the machine, where sine delta is the sinusoidal angle of the say power angle sine delta. So this is the we can write from the say impedance diagram. So in impedance diagram we can write I is equal to V by Z, but here we have the minimum, or we can say negligible rotor resistance, and the resistance of the synchronous machine. That's why we are neglecting the resistance of the synchronous machine. We are considering only the synchronous reactance of the machine. So that's why I is equal to instead of V by Z, it is E by XS, and sine delta is the angle which is the which is the power angle. Now from EF sine delta, if we make it as a subject, then this equation will become Ia XS cos theta. Now this is the value that we put over here. I is the P by Vt into XS is equal to constant, since P is equal to, we know, EV by X sine delta, so Vt EF XS sine delta. Now let us consider from this equation case number 1. If we consider a synchronous motor, then certain assumptions that we need to made before we derive or solve the power factor, or we can say power factor control using the synchronous machine. Now generally motor is connected to the infinite bus for the power factor correction, and that the voltage and frequency remain constant independent of the power exchange between the synchronous machine and the bus. So it describes that the motor which is connected with a system where the voltage and frequency remain constant, and that will become that will remain the independent of the power exchange between the synchronous machine and the bus. Now the power is constant, so we can write the equation from the previous the theory that we derived, that is P is equal to Vt EF XS sine delta, where Vt EF sine delta is we can say P is equal to Vt into Ia cos theta. So we can write both the equation for power, so in terms of the EV by X sine delta, and in terms of Vi cos theta. Now as Vt and Xs are the constant, since the synchronous motor is connected to the infinite bus, so when we connect synchronous machine with an infinite bus system, then the terminal voltage Vt and the synchronous reactance will remain same. Now from this, the EF sine delta is equal to Ia XS cos theta is equal to constant, because we have connected our synchronous machine with the infinite bus. Now the same assumptions are made for the synchronous generator. Let us discuss the theory related to the assumption. Now here you can see that the two modes of the excitation of the synchronous motor. Over here you can see that this is the normal excitation phasor diagram, and this is the under excitation phasor diagram. So over here you can see that you are getting the value of ef2 is means the angle between ef2 and say vt is say reducing in the case of under excitation, and the delta angle between say ef and ia is say constant due to the normal excitation. Means over here you can see that the angle difference between these two. So for different values of say field current, the ef will change. So these are the values that we are getting: ef1, ef2, then ef3, then ef. So this is the point at which when the synchronous machine will perform, this is the point is called the is called the normally excitation. But means below this we can say normal excitation, we get the phasor diagram is say ef1, ef2, ef3. These are the under excitation mode, and this is just because that this is just that we get with the help of the different excitation current of the synchronous machine rotor. Now as we know that the equation of the synchronous machine that we already derived from the previous theory, that terminal voltage is a combination of the field emf, emf plus ia jia access plus ia ra. So here this is the monitoring action, that's why this is the equation: vt is equal to et plus this. Now considering ra is equal to 0, because here we are neglecting the effect of the say armature resistance. So that's why the equation will become vt is equal to ef plus I a access. Now where vt leads et by at angle delta, so vt generally leads et with an angle delta. The phasor diagram of this above equation that can be described over here. So as I already explained this phasor diagram, so over here in this phasor diagram, this is the phasor diagram of the normal excitation, and this is the phasor diagram of the under excitation. So when we under excite the motor, it will behave differently, and we over excite the motor, it will behave differently, and we under excite or normal excite the synchronous motor, it will behave differently. So let us discuss how it will behaves after the when we give the different modes of excitation. So this is the third excitation, that is the over excitation. So till this means below this line we have the under excitation mode with different values of the field current, and these are the under excitation. Now this is the normally excitation mode. So over here you can see that the straight line which indicates this is the normal excitation mode, and when you get the ef is say greater than the vt, so it is called the over excitation mode. So over here you can see that the ef is less than the vt, and both are similar. ef and vt both are similar at the normal excitation, and ef is greater than vt, then it is called the over excitation mode. So in over excitation mode, this will get by exciting the rotor circuit with the help of different field current. Now these are the modes, and through this we can plot the v curve of the synchronous machine. So let us discuss the v curve of the synchronous machine. So over here you can see that the v curve is proportional to say ia is the y-axis and if is the x-axis. So on ia we have the on y we have the armature current, and on the x we have the field current. So for different value of the field current we'll have the value of the armature current. So when the field current say under excitation mode, at that time the armature current is say quite much high, and as we increase the field current at the normal excitation mode, gradually the armature current will reduce, and the speed of the motor will increase. So the armature current as reduced, up to a certain value of the field current, the armature current required will be less, or we can say negligible. At that time the motor say speed is synchronous speed, and when it is get overexcited, and as you will increase the field current again further, then after the motor armature current requirement will increase. And this three modes describes the behavior of the synchronous machine. So whenever the machine is under excitation, the it absorb, or means it will behave like an inductor. The power factor is lagging, means of the synchronous machine. And whenever the normally excitation and machine is normally excited, at that time the power factor is will become unity. Practically it is not possible, but we are considering the theoretical efforts that put over here. When field current is at the normally excitation mode, at that time the synchronous motor will behave like a resistive circuit, so the power factor is unity. And then after, if we increase further the field current, the motor will behave like that. The power factor of the induction synchronous motor will increase, and it is called the leading power factor. So this is how we can plot the V curve for different field current of the say rotor field circuit. And with the help of with the different field current, we can excite our synchronous machine in three modes, say normally excited, under excitation, and over excitation. By getting three modes of this excitation, by giving this three modes of excitation, we will have the performance of the motor, say lagging, and then unity, and the leading. So by using this modes of excitation, we can control the power in the transmission system by using this synchronous machine as a end condenser, or we can say synchronous condenser in the power system. And we can improve the efficiency of the transmission line, and we can maintain the voltage regulation of the transmission line after exciting, or we can say giving excitation to the synchronous machine, and operate the synchronous machine in this three different way. Now this is the case number 2, for which we are going to discuss the synchronous generator. We have this generating action, that's why the equation of the terminal voltage will change. So in the previous case, the equation was Vt is equal to Et plus the losses. Over here the Vt is equal to Et minus the losses, where Ra is the armature resistance. Over here again we are neglecting the armature resistance, and we are putting Ra is equal to 0. Now Vt is equal to EF minus JIA excess, because we have considered this RA is equal to 0, where VT lags ET by the angle delta. So these are the modes of the excitation. This is the normal excitation, this is the under excitation. This diagram is similar to the synchronous machine, but only the difference is you are getting this vector diagram in the say third and fourth quadrant. So over here you can see that this is the angle, or we can say phase angle, or power angle delta, which is across the between the EF and IA. So VT is the terminal voltage, and EF that we means generated after the subtracting the losses. Now this is the under excitation, in which you can see that this is the line, is the line for the normal excitation, and below this line means where you get the VT is less, means EF is less than VT. This mode is called the under excitation mode, or it is called the leading power factor mode. And this is the mode at which we get the unity power factor. Now this for the different field current, means for the different values of the field current, or we can say for the different values of the excitation, we will have the value of EF1, EF2, and EF3 and EF. So once we reach at the EF, it is called the normal excitation of the synchronous machine, and this is the under excitation mode of the synchronous machine. Now the phasor diagram of this equations are this normal excitation, under excitation, and the third phasor diagram, that is over excitation. So in over excitation you can see that the effect of the over excitation, if we give the field current say more than the normal excitation, then the EF will get increasement. EF greater than VT, then it is called the over excitation mode. So from this graph you can see that when the EF is equal to VT, at that time that mode is called the normal excitation, and when EF is less than the VT, then it is called the under excitation mode, and when EF is greater than VT, then it is called the over excitation mode. So in this modes of the different modes of the excitation methods, we will use our synchronous machine for the different working purpose. So over here from the V curve you can see that this is the armature current IA minimum at the unity power factor. So the armature current requirement at the unity power factor is minimum. So again we have taken IF is at the x-axis and IA is at the y-axis. Now for different values of the field current, means whenever the field current is normal or under excitation mode, at that time the armature current requirement will be more, and as you gradually increase the field current, the armature will gradually decrease, and after a certain time, means at the point where we reaches up to the normal excitation mode, at that time the armature current IA will become minimum, or it will not get completely zero, but armature current requirement will get zero, and the field current is say at the normal excitation mode. And when you further increase the field current from the normal excitation mode to over excitation mode, then the armature current requirement will also increase. And over here you can see that the in the normal excitation mode the machine is behaving like say a resistive circuit, purely resistive circuit. So its power factor is say unity at IA's minimum, IA minimum is the requirement at that point, and the power factor is unity. And in the case of the under excitation, over here you can see that the synchronous machine or generator will behave like a say leading power factor, or we can say it will behave like a capacitor. And over here you can see that at the over excitation it will behave like a lagging power factor. So this is the mirror image of the synchronous motor. So in the under excitation mode, the synchronous motor will behave like a lagging power factor, and the synchronous generator will behave like a leading power factor. And whenever the excitation is say normal excitation, at that time machine will behave like a resistance, and whenever the machine is get over excited, in the case of motor, then it will behave like a lagging power factor, and in this case it will be sorry, leading power factor, and in this case it is behaving like a lagging power factor. So this is the difference between synchronous motor and synchronous generator operation for different say values of the field current. So let us discuss that another important operating condition is say variable power and fixed excitation. In this case VT and EF say both are fixed, and while delta and the active power vary is say accordance with the equation P is equal to EV by X sine delta. So according to this equation, the load angle, or we can say power, active power, and that get varies. So the corresponding phasor diagram for two values of delta is shown in this figure, and it is seen from the diagram that as the delta increases, current magnitude increases and power factor improves. So as we increase the delta, as we increase this delta, and the current magnitude will increase. So this is the current means this is the current that will get increased, and and the power factor improves. So power factor where the power factor improves, if the magnitude of the current will increase, that the ultimately the power factor means of the between V and I will get increased. So that from this vector diagram you can see that this is the terminal voltage VT, it is taken as the reference. Now here we have to means neglected the effect of resistance. That's why there is no resistive circuit, means resistive circuit drop is mentioned over here. So in this you can see that the IA1 and IA2 are the currents for different means power factor angle, that is theta 1 and theta 2. So as you increase, means this is the first level at which we are getting the value of EF, that is the delta 1. But as you increase the magnitude of say the delta, means if you increase the delta angle between V1 and ET, if you increase, then so as the power factor angle theta 1 will become theta 2, and for theta 2 you can see that the angle between VF and IA2 will get reduced, and so as the power factor will improve. So this is how we can improve the power factor of the synchronous machine, by changing the excitation angle. So here you can see that the terminal voltage VT is having the IAX, means IS2 or IA2 excess drop. So this is nothing but the reactive drop of the delta 2, because we are changing the excitation, and we are changing the phase angle by changing the excitation of the machine. So you will get this EF is equal to V1 plus GIA2 excess. So this is the operation of the synchronous generator with variable power and fixed excitation. Now this is the topic number 6 of lecture number 4, that is salient pole synchronous machine. Let us discuss the salient pole synchronous machine or synchronous generator. Now let us discuss the salient pole synchronous generator. So what do you mean by salient pole? Salient pole means this is the structure of the say rotor, and it is looking like a dumbbell. So in this generator we have the less number of pole compared to the cylindrical rotor. So such kind of generator are used for the high speed. So in the case of thermal power station, generally we use such a generator for the generation of the power. So in this are the number of pole. Over here you can see that this is the 4-pole generator, and in this we have the less number of pole, but the speed of the armature, or we can say rotor, we can have say, if you rotate this rotor with high speed, the same amount of power can be generated. Then the difference between salient pole and synchronous is synchronous rotor is wounded, and in this it is wounded, but in this we have the say less number of pole. And pole periphery, or we can say rotor surface periphery, is in this we have, you can see that this is the area at which we means the this generator will offers the maximum reluctance, and at this area it will offer the minimum reluctance. But in the case of smooth cylindrical rotor generator, the we can say reluctance between stator and rotor, means there is a uniform gap between stator and rotor circuit, so that it will offers the less reluctance. But means the cylindrical rotor is generally we use for the hydropower station, and means having means weight of that rotor is more compared to this type of rotor, and the that rotor rotates is around 150 rpm, means 150 rpm, and that will produce the same amount of power after the rotation, because it has the large number of poles compared to the salient pole machine. Now salient pole synchronous machine, it is distinguished from the round rotor machine by the constructional features that I already discussed, and features of the pole which project with a large interpole air gap. So over here you can see that this is the interpolar air gap, and salient pole machine analysis is made through the two reaction theory that we already discussed in our electrical machine. So over here you can see that these are the factors that that describes the working principle of the salient pole machine. So in round rotor machine, the armature current is in phase with the field current EF. So it is at the, we can say, at 90 degree or we can say at the quadrature axis to the EF. That's why the in phase or quadrature current is say XA plus XL is equal to XS. So this is the synchronous reactance that become the resultant of XA armature and XL. Then after the salient pole machine, air gap is non-uniform along the rotor periphery. That's why it has two axes. One is quadrature axis and one is the direct axis. So direct axis is means quadrature axis is called the least along the axis of main pole, and the largest along the axis of the interpolar is called the quadrature axis. So direct axis is in another word we can say direct axis is the polar axis. So whenever the pole placement is shown in that say diagram, you can see that if that machine is having two pole, then if you draw a line which is passing through the pole is called the direct axis, and the means perpendicular which is perpendicular line which is passes through the center from the rotor center is that will become the quadrature axis of the synchronous machine. Now armature current is say in quadrature with EF produces a flux along a direct axis, and that reduces the flux path being low because of the small air gap. So air gap is smaller, that offers the least reluctance, and it produces the large flux leakage per ampere, and hence the machine presents larger armature reactance XD, that is called the direct axis reactance, and to flow of the quadrature axis component ID of the armature current IA. So this is the working principle of the salient pole machine. And on the other hand, you can see that armature current in phase with the EF that produces the flux along the quadrature axis, and the reluctance of the flux path being high. So in the case of the, as I already explained, the quadrature axis having the say large reluctance, over here you can see that this is the quadrature axis. Over here you can see that this is the point from which this is the distance to the rotor. So air will offers the maximum reluctance to the flux lines. So this is the portion at which the maximum air gap. But over here direct axis, it is the polar axis. You can see that there is a least air gap between the stator circuit and the rotor circuit. So that's why that will offer the minimum reluctance to this circuit. Now since the salient pole machine offers the different reactances to flow, so ID and IQ components of the armature current IA, a circuit model cannot be drawn. So from that we can have the phasor diagram of the salient pole machines. Over here you can see that the output is the combination of say V plus IARA plus IDXD plus IQXQ. So this is the addition of the quadrature axis and direct axis reactances, and direct axis quadrature axis drop. So from we have the armature current IA, and here we drawn the two axes, that is one is current is ID and this is the IQ current. So both are at 90 degree to each other, and this is the resultant current of that ID and IQ is armature current IA, and the angle between the E output and the IA is say psi, and uh, over here you can see that the angle between E output and V is the delta, or we can say phase angle. And if you draw a resultant triangle of this, then you will get the point at which the point C. So this is the triangle from you can solve the all the parameters of the salient pole synchronous machine. Now in the line of IA, the IRA drops will take place, and this is the reactive drop that will take place. But this is the resultant diagram of all this means the plottation of the quantities, means plotting of the quantities. So over here you can see that OV means suppose you put OA, then OA is the combination of OV plus IARA, and after a2, supposing here if we give d, then a2d is the id xd, and this is the b2c is iq xq. So from that we can write the equation of e output of the generator using this phasor diagram. So from the above diagram, the tan psi, if you want to write the equation of tan psi, so tan is the sine upon cos, so v into sine theta plus I a x q, and then IARA. So for the lagging power factor, tan psi is the V into sin psi plus IA xq divided by V cos psi plus IARA. And for power angle curve for the Salient pole synchronous machine, the neglecting the armature resistance, if we neglect the armature resistance, the diagram will become like this. In this diagram you can see that this is the phase angle between V and EF, that is delta, and V and I is the power factor angle. So from that we can determine the value of say E is equal to V plus ID XD plus IQ XQ. So from the figure we can write the equation E is equal to V into cos delta plus V into cos delta plus IDXD. So from ID we can determine that E minus V cos delta divided by XD, and where V sin delta is equal to IQ so IQ will be the V sin delta divided by IQ. So this is the equation number 1, and equation number 2 that we get from the power angle curve for the Salient pole synchronous machine. Now P is equal to I into the components of the voltage along d axis plus iq into components along the voltage along the q axis. So here from the we'll get the resultant of all the components at the d axis and q axis, and we will get the value of the power. Now substituting equation 1 2 in this, so the values are E minus V cos delta divided by XD into V sin theta plus V into sin theta divided by XQ, so that is V into V cos theta. So this is the equation of the power. Now from that if we solve further, then the p will become the after putting the direct axis and quadrature axis reactance, and after solving this the answer means the value that we derived from the solution is ev sin delta divided by xd plus v square by 2 1 upon x cube minus 1 upon xd, so into sin 2 delta. So the first term is called the electromagnetic power, and the second term is quite small, about 10 to 20% compared to the first term, and it is known as the reluctance power. So the p versus delta is plotted over here. You can see that this is the delta and this is the p. So for that the waveform is plotted. So it is noticed that the maximum power output occurs at the delta less than 90 degree, also about 70 degree. So further dp by d delta change in the power per unit change in power angle for small, then changes in the power angle called the synchronizing power coefficient, and the operating region delta is less than 70 is larger in a Salient pole machine than in a round rotor circuit. So over here it is described that this is the power and this is the load angle delta equation, I'm sorry means a graph, and from that graph we can say that and at the delta is equal to say less than 90, we will get the maximum output of the synchronous machine. Now let us discuss the operating characteristic of the synchronous generator. I think the lecture will become more lengthy if we consider, if we include this topic in this lecture. So we are keeping till this. So thank you student, thank you very much all. If you have any doubt or any query related to this topic, so we can solve your doubts and queries in our doubt solving session, and we will I will give you the assignment and worksheet question related to this topic once we finish this topic. So thank you very much student, thank you very much all. Jai Swaminarayan.